Okay, so today our general topic, we want to talk about series. Let's start off and give maybe 10, 15 minutes, and let's talk about a few things that I saw on the midterm, primarily with sequences, and maybe brush up on some of the smaller points on sequences that we didn't quite have time to go over. Primarily, we had a question about bounded sequences. So, important things that I saw on the midterm, and this is rather scary to see in a Calc 2 class. But what is the derivative of an exponential function whose base is not e? Any takers on this one?
2 to the x ln 2.
Yes, 2 to the x times natural log of 2. So this came up on one of the sequence problems where we had to do L'Hopital's rule. This appeared in a ratio. And some people tried to do L'Hopital's rule and ended up writing something like the derivative and this is terribly wrong. So be careful with that. Might have just been a brain fart in the haste of the exam. So some other topics on sequences. So we say that a sequence is bounded if there exists real numbers we'll call them little m and capital M, such that the sequence always fits in between these two numbers. So this kind of showed up on the exam as well. We've seen this, for examples, with something like cosine of, say, n pi over 4. We can show, we can just say properties of cosine. Let's call this sequence an. We know that an is always going to be between minus 1 and 1, since cosine is always going to be between minus 1 and 1. So this is bounded. However, we need more information to determine convergence. Just because a sequence is bounded doesn't mean it converges. So you do got to be careful with these arguments. There was this example on the exam, and some students bounded it, and then some weird things happened with these minus ones, and some people were trying to use a squeeze theorem to find the limit. So you have to be careful with the squeeze theorem. You need both of these upper bounds to ultimately be the same. So sometimes you can bound a sequence by two other sequences, and if those two sequences converge to the same limit, then the middle sequence will have to converge. This is a little bit more, this is more advanced than just a general boundedness argument. Bounded just means that we have constants for which the sequence will always lie between. So pictorially, what's going on with bounded sequences? we have our sequence. And it could do something like this, where it oscillates. And what we can say is that this guy here is our little m, and this guy up here is our capital M. So essentially a bounded sequence means we can put it in a strip, so to speak. It's like putting it in a box, or at least a vertical box, where we have two values that it's always going to be stuck in between. It'll never go outside. So some properties: convergent sequences are always bounded. So if the sequence converges to a point, it has to be bounded. There's going to be a max and a min somewhere. Sequences that are unbounded are divergent. So if this is what bounded means, that we're always stuck in between two lines, or the values of the sequence are always going to be, there's an absolute max and an absolute min that we will never break out above or below. Unbounded means that there is no absolute max or there is no absolute min. And so if either of those situations occur, that means the sequence, at least some subsequence or some values of the sequence, are always going to become bigger and bigger and bigger. And if it always gets bigger and bigger and bigger, it will never converge to a single value.
Can you have it so that you have one bound but not another? So no maximum, but maybe a minimum.
What'd you say? Sorry, say that again. What
So
I have here, or
could you have like a minimum value that it never goes below, but no maximum value? So it can be bounded on one side.
Yep. So you can have sequences that look like, let's say for all even terms, the value of the sequence is 0. But for all odd terms, it grows. You can just have it grow linearly. So the sequence goes, it zigzags, and some of the terms are getting bigger, but then we have an absolute minimum. So it's bounded below by 0. Sequence never gets below 0, but there is no maximum. It just keeps getting bigger and bigger.
Just a quick question for notation's sake. Little m refers to minimum and big M refers to maximum, correct?
Yeah, that's what I'm using.
Awesome, thank you.
And then we do have a theorem. Actually, we haven't talked about monotonic sequences. Let's touch on that real quick. Monotonic. Monotonic sequences just means increasing or decreasing. So you guys saw some of these, I believe, on WebAssign. And how do you show that? Well, there's a couple ways. Sometimes you have to show it explicitly by comparing consecutive values of a function. Or you can just, if you have a closed form expression and you have a function that can represent the sequence, then you can take the derivative of the function, and if you show that the derivative is positive for all values of x, then the sequence is increasing. So for example, let's say we have an is equal to 1 over, let's say 3 plus n. So for f of x equal to 1 over 3 plus x, we can take that derivative, f prime of x is 1 over 3 plus x squared times a -1. Now, this sequence, we should have had a starting value somewhere, or it should have been indicated, let's say for n bigger or equal to 0. Because that starting value is going to represent the domain of the function, which is always going to be 0 to infinity, 1 to infinity, depending on the starting integer of the sequence. So we know here our f prime of x looks like this. And then likewise, how do I analyze this in Calc 1 terms? Well, we look for the zeros, and there are no zeros since the numerator is never 0. And the only asymptote is over here at -3. But if we pick any value, so if we do our test point of x equals 0, what are we going to get? We're going to get a negative value. So we know that f of x is decreasing for all x from 0 to infinity. And so if I have a function that's decreasing everywhere and the values of that function of an lie on that function, so we know that an is decreasing. Alternatively, the way you can show this, is everyone done writing? Are people still scratching stuff down?
Yeah, just a quick question from your messages here. You have for increasing and decreasing, you have the same like thing written out as an plus 1 is greater than. So is that supposed to be flipped?
Yeah.
Okay, thank you.
Yeah. Next term is greater than the previous term. Decreasing, the next term is less than the previous term. Sorry about that. So a decreasing function and a decreasing sequence are essentially the same thing. Of course, we've seen sequences that we can't model by functions. This is another point that I saw a bit. There seems like there's still some confusion on factorials. Some people were trying to use L'Hopital's rule and take derivatives of factorials. Factorials you cannot use for x for continuous functions. It doesn't make any sense at this level. So if there's factorials and things like that, we have to do a little bit more. If our an is something like 1 over, let's just do something basic like 1 over n factorial, we can't take derivatives. So what we have to do is do 1 over an plus 1, which looks like that. And we want to compare with our an. And so now we've got to use our algebra skills to show that this term is always going to be bigger or less than this term to show that it's monotonic. So one way to do that, or at least how I like to organize my work, you put a little box here. Let's put a little dash box because we want to put a greater than, less than, or equal to, and we want to compare these two. Which one's bigger? This might take a little practice. So you got to do some algebra to compare this and manipulate this guy into a form where we can compare it to the previous term. So I usually like to start with the next term, this an plus 1 term. And of course, sometimes we have squareds, other exponents. And so you got to use the algebra of all of whatever operations are being performed on this n+1 to simplify it in such a way that it looks similar to the previous term, but with the modifications giving a clear comparison. So for
I have a
example,
question.
yeah.
Couldn't you set them up as like not fractions and then you can compare them and then put them as a fraction and then that would determine which one's greater and less than? Or can you not do it like that?
You mean compare like the denominators separately?
Yeah, like if you put it to n+1 factorial and compare it to n factorial, obviously n+1 is going to be greater than, but if you both put them as fractions, then the integer would flip. So then that would mean 1 over n factorial is greater than 1 divided by n+1 factorial. Or
Yeah,
not? Okay,
that's one
I
way to
wasn't
do
too
it.
sure if you could do that.
You can, you just got to be careful. You may want to make a statement that since the numerators are the same, all we have to compare is the denominators.
I see, I knew there was something to it. That's why I was like, I don't think that's an exact way you could do it, but that's why I wanted to ask. Thank you.
Yeah, but that's exactly like some of the thinking we were working with last week, is that when we want to compare sequences and use what we were using, you were using comparison tests essentially, and this is, it's essentially like doing a comparison test with these guys, except you're just comparing itself, the next term, to itself. You got to compare numerators and denominators. So one way is to show, yeah, the denominators, one denominator is always bigger than the other, as long as the numerators are the same. So if the numerators have different sequences up there, you got to mind that comparison and those effects on the comparison as well. Yep. So essentially this comparison, you can see this, and clearly we have 1 over n factorial, and here's a 1 over n factorial, but we are also multiplying it by something that's always going to be positive, especially since our n always bigger equal to 0. So I know that because this denominator is bigger, we will always have a smaller fraction. So from that, we can conclude that an+1 is always less than an. So it's decreasing. n=1 and n=0 are the same for that example. So would it be monotonic? Good question. Yes. So monotonic, there's some slight words that mathematicians use to describe these. So notice that I said an+1 is bigger or equal. So a constant sequence, we technically could consider as increasing, but it's also considered as decreasing. So as long as the values don't decrease, don't strictly get negative or get smaller, then we can consider it as increasing. So even if we have two terms that are the same value, like in factorials, when we have 0 factorial and 1 factorial, right? If we were to write out the sequence, 0 factorial is 1, 1 factorial is 1, and then we have the factorial growth in the denominator. So even if, like, between these two terms, it didn't decrease, but it also didn't increase. So as long as they're equal and then decrease, that's fine. We still say it's decreasing. If we say strictly decreasing, so we add that word strictly, that means each consecutive term is strictly less than and not equal to the one before it. Okay, and so the last theorem for this is our monotonic convergence theorem. I keep spelling that wrong. Convergence theorem. A bounded monotonic sequence is always convergent. So boundedness is not enough to show that it's convergent. However, it is bounded and monotonic, it will converge. Basic idea behind what's going on here. Well, if I have a bounded sequence, I can always find a minimum and a maximum. And then the sequence has to lie in between there. But now if it's monotonic, let's say if it's always increasing, no matter where it starts at, it's got to increase. And so since I can't decrease, I can only get so high, but I also can't break above this line. So there has to be at least some point. It may not be that exact upper bound unless we're careful about choosing the least upper bound, but the sequence has to essentially level off and approach a single value, meaning it'll converge. Okay, let's talk about series real quick, and we're gonna have to get through this fast. These Tuesday and Thursday lectures are unfortunately quick because of recitation. So maybe Lewis can kind of pick up a little bit where I left off and do some more practice with you guys on series. Series. And I can't spell today. So given a sequence, series, just ask, can we add up all the values? So for finite sequences, so you can essentially think of a finite sequence as just a finite collection of numbers. We write things like 1 plus 2 plus 3 plus 4 plus 5. Let's say I want to add up the first 5 numbers. If I were to write up these terms as a sequence, if I say an is equal to, let's say n, starting with 1, well, this will give me that sequence apart from the sum. Sorry, let me put that as a set. So how do we express this sum? We use this letter, Greek letter sigma. And then on the lower, we put our starting number for the sequence. And then on the upper here, we would put our maximum number. So we can also fill in the actual closed form expression of the sequence. And even though the sequence might have more values, if we only want to add up a finite number of them, n equals 1 to 5. Conversely, we can add up more, and we can write something like the sum of, let's change it a little bit. If I say n squared, starting from 0 to, let's say, 6, that means 1 plus 4 plus 9, 16, plus 25, plus 36. So given a sequence, we can create a new sequence called the sequence of partial sums. Given by So whatever starting value, I like to start at 0. Wherever the starting value of the sequence is. Most sequences are going to start at 0 or 1, though we can start at higher numbers, 2 or 3. And so what this just means add up the first n terms, the first capital N terms of the sequence. So for example, in this one, we could call this capital S sub 6. And this one, we could call this capital S sub 5 of the sequence AN, and however AN is defined in each individual case. The infinite sum aka the series, is then, we usually just denote it by S. And this is the sum, the infinite sum of all of the terms in the sequence. So we add up to infinity. And how do we compute this? We'll have various techniques, but to be rigorous, we would compute it as taking the sequence of partial sums and then computing the limit of that sequence.
So why is the N capitalized under limit instead of like lowercase?
Because that's the independent variable that we're using for that sequence. The sequence of partial sums has a different independent variable.
All right, thank you.
Okay. So some examples. And actually, I guess, so our last definitional statement, if this value, the sum of everything, is finite, we say the series converges. If it's infinite or does not exist, then it diverges. So some examples. Any finite series will always converge. We can always add up a finite number of terms. So this is just 1 plus 2 plus 3 all the way up to 100. How do we add up all those numbers? Anyone have any ideas? 5,050, how'd you get that?
Wouldn't it just
Oh,
be
you
one-
pair them up. 1 and 100 make 101. 2 and 99 make 101. So if you keep doing that, then you have 101 multiplied by half the number of terms. So that's going to be what, 50.
Yep. So if we add 1 plus 100, I guess the way I was going to do it was divide by 2 and then times 100, but we will get the same thing. So this guy, this is our average term. Why is this our average term? Well, if we were to add up all the numbers and then divide by the total, right? 1 plus 100 divided by 2 gives me 55. Or not 55, 50.5. And of course, 2 plus 99 will give us the same thing. So that's going to be our average term times the total number of terms.
An easy way to look at it is if you just start writing out the sequence, I guess, above or below the normal sequence, but backwards. You see how they pair up.
Yep. So there's going to be some formulas. I recommend you guys checking these and proving these on your own. Of I equals, let's say 1 to capital N. Of course, I is just going to be n plus 1 over 2 times n. And in general, for any linear sequence, we can come up with fairly easy formulas for the nth partial sum. Of course, the limit of that as it goes to infinity is going to be infinite. Of special note, some special types of sequences. These are, of course, linear sequences, give us linear series. We can have a constant series. So if I have something like this, if I just write 5, so I change the independent variable to I, k, and lowercase n, all very common for our index variable. So when I say index variable, independent variable, it's the argument on the sequence. It's our spot index of what placeholder we're at in the series. So if that doesn't appear, this just means 5 plus 5 plus 5 add up an infinite number of 5s. So of course that's going to give us infinity. That one will diverge for sure. And then the primary one we want to look at today, at least in terms of convergence, are going to be geometric series. So what's a geometric series going to look like? Of course, when I plug in n equals 0, we are going to have a. Our next term is going to be plus a r, a times r, excuse me, plus a times r squared, plus a times r cubed. And that's going to go on to infinity. So one of the things we will see with series is just like integrals, we can always pull out constant multiples. So of course, in this term, we just wrote that out. We had AR, or A plus AR squared plus AR cubed is what this notion means. Of course, in that previous writing, we could, at least for any finite sum, I can always factor out that factor of a. And essentially what we have now is that we can, even if it's an infinite sum, we can consider pulling out that constant multiple of a. In other words, we can add up 1 plus r squared plus r cubed, do all that sum first, and then multiply the answer by a. And so our question with these guys is what values of r will give a convergent series? And so let's do this a little more formally now with our proper definitions of the sequence of partial sums. So this we mean the limit as our partial sums go to infinity. So I only add up the first capital N number of terms, and then we want to take that limit to infinity. We know how to compute limits of sequences now. And so let's write a little bit of this out. So S sub 0 just means that we have a. S sub 1, a plus ar, sum from 0 to 1. S sub 2 is going to be our sum from 0 to 2, a plus ar squared. Likewise, as we keep going, our S sub n, a plus ar squared plus ar to the capital N. So in other words, we can write our sum as this. And so now our question is, when will this converge? Or can we come up with a better expression for S sub n? And so the trick with geometric series is to note that r times S sub n is going to be equal to ar plus ar squared plus ar cubed since we are multiplying by a constant multiple. If I multiply this entire series by r, it looks very similar. And in particular, if we take, I think it's commonplace to do it this way, to do Sn minus r times Sn, well, that's gonna, what's that gonna give us? So we're gonna have Sn minus this guy. So the A doesn't have anything to affect it. However, this AR minus this AR are going to cancel. This AR squared minus this AR squared are going to cancel. All the middle terms are going to be subtracted from each other. This AR to the n will subtract off and cancel with the AR to the n in this term. However, this n term in our subtraction doesn't have anything to pair with. So we are doing some algebraic manipulation to come up with a better defining equation for the nth partial sum. Essentially, we can write this down as our nth partial sum, but what we want is a closed form expression for the nth partial sum. This is sort of more abstract sequence notation, especially with the dot, dot, dot. We cannot manipulate that very easily algebraically. However, now Sn is a sequence of partial sums. It is a number. It will always be finite for partial sums. So we can factor that out. And let's go ahead and factor out this A as well. And we can show that the sequence of partial sums for a geometric series satisfies this equation. And so our original question is, what values of R will give a convergent series? Well, now we have that the sequence of partial sums is given by a closed form expression. And so now the equivalent question or we can rephrase that original question by asking what values of R, say 4, what values of R will the sequence of partial sums converge? So we want to know, when will I get a finite limit in this case? And so hopefully everyone can see our answer. Looks like we had a good guess in the chat. R less than 1, but we also want to consider negative values of R as well. So if you're just thinking positive, good guess. Yeah, good answer. Absolute value of R less than 1. So we saw our geometric sequences in the last section. And of course, if the multiple that we're using to get the next consecutive term, if the absolute value of it is bigger than 1, or if it's bigger than 1, we know that the exponential sequence will just grow exponentially. If R is less than 1, then the exponential sequence will decay exponentially. We also want to consider the potential of having a negative value of R, so that'll just give us an alternating sequence. And if we are able to compute that limit, well, if R is less than 1, well, when I raise that to the infinity, it will vanish. It will go to 0. So this term over here will go to 0, and we will be left with this guy here. Example. Find, let's do 2 to the n plus 1 over 3 to the n minus 1, n equals 0 to infinity. Now, what's our problem with this guy is it looks like a geometric series, but it's not quite in the format we want. How can we identify it as a geometric series? Well, the numerator is a geometric series, 2 to the n. plus 1 is just going to shift our starting value. The denominator is a geometric series. 3 to the n minus 1, again, just shifts the starting value. So our step 1 with these guys is going to be put in this form. So our n equals 0 to infinity. I have one extra power of 2 here. In the denominator, I actually need to add in, I want a 3 to the n in the denominator. So let's actually throw in an extra 3 in the numerator so that if I cancel those two, we would have n minus 1 in the denominator. So this is just how we work with our algebraic manipulations. We've got 2 times 3, and now we've got 2 to the n over 3 to the n, which we can write as, I'm going to go ahead and pull out the 2 times 3. We can multiply those and pull them outside of the sum. And this is just 2/3 to the n. So this guy is our r. That's our a. And so now we can use our formula to compute the limit of that sequence. Any questions?